In this assignment, we will explore different algorithms for flow routing and watershed analysis. So let's first create a new map set for this assignment. And let's call it assignment 7. Okay. And let's also cd to a directory where we will put our results, our resulting images. And I will create a new folder for that. And switch to it. And I will also download this text file with just a single point that I will need later on for delineating contributing area. And I will save it into this new directory. Okay, so now we are ready to start. So first, we will derive direction of flow, flow accumulation, and delineate watersheds for our study area. And our study area will be from our standard data set in Southwest Wake County. And as a first step, we will set the region to the digital elevation model that we will be using. And then we will run command r.watershed on this digital elevation model to derive flow accumulation, drainage direction, and basins. And we select threshold of 10,000 cells for the size of these basins. We also have here a -s flag, which tells our r.watershed command that we want to use single flow direction algorithm. So let's set that region. Now let's run the r.watershed command. So you can see I got this mysterious blue rectangle here, but so think about it. What do I need to do? I need to zoom to my computational region. So now I can see those watersheds, those basins that were derived. This is the drainage direction. And if you have listened to the lecture, we discussed that the drainage direction is essentially a steepest slope direction, which is aspect. So that's why it looks very much like aspect. But because it is only D8 algorithm, it's much more discrete than the aspect that we get from our slope aspect command. And this is the flow accumulation. So now we can use flow accumulation to extract streams. And the simplest way how to extract potential streams is through a threshold where we will extract all the grid cells where the flow accumulation is greater than 100 cells. So let's just grab this set of commands. So we will use map algebra to extract those cells, and then we will convert them to vector representation, and we already did that very early in this course. So you should know what is going on there. Now you can see, just recall that when you run rmapcalc command, it doesn't add the output automatically to the to the display and to the layer manager. That's because very often our map calc outputs may be some preliminary results or results that are not final yet. So you can add it using this add raster, so we can display this output. But make sure to switch off all the other layers so that you can see these are the extracted streams, and you would have to change the color table to get them in darker color. So, but let's just convert them to vector representation. And we will convert not only these streams to vector representation, but also the basins, which we have in this layer. So this is the vector polygons representing the basins. Then we will thin the raster streams. That's the thinned streams, very close to what the original extracted streams were. And now we will convert them to the vector representation. And now let's just clean up all these layers that we have here, and let's create some nice maps for comparison with the provided stream map and for our report. So we will erase these intermediate layers. We will display the basins over shaded topography. So we are using the HIS command for that. Then we will highlight the boundaries of the basins. Then we will include the lakes, and you can change the color table on the lakes if you want to highlight them a little bit more. Then we will add the vector representation of streams, and let's just save this map with the extracted streams for our report. And now we will overlay our streams with the streams that are provided in our dataset. And these streams were derived by digitizing from high-resolution orthophotos. And let's save this layer in our database. And then to answer the question about the comparison between these streams, then I suggest that you zoom in so that you can see the differences a little bit better. We can just zoom, for example, here. And what you may notice is one is the positional accuracy, and another thing is some of these little ones, streams are missing. So now you need to find out how can you modify the map algebra expression so that you get more of these smaller streams in your extracted stream layer. So that would be the task for you to do. Now, let's just zoom back. Now, another feature that we will look at are DM depressions. As you might have noticed, we didn't have to fill any depressions to extract the streams and to compute the flow accumulation. And that's because the R.watershed algorithm is based on least cost path. So we don't need to modify the topography to actually get a continuous connected stream network. But you may have in some other software packages, or when you are running some other hydrologic models, there may be a requirement to fill the depressions. And I just want to show you with this part of the assignment how much you would be modifying the topography and how problematic this step is. So let's just use the same spatial region, but we will do this analysis with high resolution elevation model. And that's the raster elevation that has 10-meter resolution that we have used many times already. So let's just set the region to this elevation. And again, the spatial extent is the same. We just have higher resolution. And then we need to, because the depressions are nested, then we need to run it several times to get the entire hierarchy of these depressions. So the first run really detects just the very small ones. And you would have to change the color table to actually see what is being extracted. So I would encourage you to do it, but this is just intermediate results. So we are not really including this into the report. Then there is another extraction. You can see slightly bigger depressions. And then with this last run, we will be extracting the biggest depressions that we have there. So you don't really see that much. You would have to change the color table. So I encourage you to do that. And now what we will do, the output of this fill is not only the depressions, but also the direction of flow, and also a DEM that has these depressions filled. And you could see it, for example, if you display this DEM in 3D, but to actually find out where it is filled, for example, here you can slightly see this is filled, this area is filled as well. So to find out which areas were filled, what we will do, we will subtract our original elevation data. We will subtract the field DEM from the original elevation data and just put whenever there is this negative difference, then we will assign 1, otherwise we will assign nulls. So let's just do that, and then we will assign blue color, and now you see all the depression, all the field depressions in this DEM. So as you can see, it is a lot of areas, and many of these field depressions are actually artificial. So let's just display them in a clean way. So we will erase all these other layers. We display the original elevation, we display the roads, and we display the depressions, and you can right away see that some of these depressions are really created by the roads, that they are blocking essentially the flow. So they are artificial because we don't have the bridges and we don't have the culverts represented in this in the DEM. And we discussed why this cannot be done. And then we will also display the lakes, and you can change the order of the lakes so that you can see how well they overlap with how well these field areas overlap with the actual lakes. So again, it's not such a great overlap. And let's just save this map for your report. And for a discussion about where do you see these depressions, are these depressions real lakes or real depressions, or are they artificial, really just by blocking the flow by anthropogenic features and so on. Then there is also a question, what is the area mapped as depressions in hectares and as percentage of this entire area? So you already have the map of the depressions, so you just need to run r.report report on that layer. And you can also compute the volume because we have computed the difference between those two original elevation and the elevation that is filled. But instead of assigning 1, you should actually put here the elevation so that you know the depth of those depressions. But that's an optional. So make sure that you have at least the area. So now we will switch our task. So here we were analyzing a larger region. Now we will zoom into our small agricultural watershed, and we will do a similar analysis with r.watershed for that small watershed, and then we will extract a contributing area for a given outlet point. But to do that, we need flow direction, and we already know that we can get flow direction from r.watershed, although it will be single direction flow direction. So we will switch our region, and we compute the flow accumulation, draining direction, and the basins. And you can see the outputs really popped up here. So let's zoom to computational region. And so this is our, let's get rid of these. Those were the basins. So this was the output basins. This is the drain direction. Again, it resembles a more discrete representation of aspect. And this is the flow accumulation. And you can clearly see the impact of the D8, that we have only 8 directions. And at this high resolution, you see a lot of artifacts in the flow routing. Apparently, those 8 directions are not enough for this particular landscape. So now we can extract the contributing area for an outlet for which I have provided the coordinates. And it was very important to put these coordinates of this point exactly on the maximum of flow accumulation extracted from r.watershed so that we get actually the correct contributing area. So let's now do that. So now we have the contributing area for a point that is actually here on that extracted stream. We will convert it to vector representation so that we can extract just the boundary. And let's now import also the outlet point. And it looks like I didn't put it into that directory. So let's skip it for now, and then we will come back to it. Because we don't really need it, we need it only for the visualization. Let me just do ls. Oh, okay, it has a different. different name. Let me fix it and then we can import it. For some reason, my download software is adding this extra one to it. Okay, now it should run. So let's run that. Okay, so now we have that point, and we will change the symbology so that we can see it better in a minute. So let's now create some maps and create a report for this small watershed in our study area. And for example, for this particular area, we actually had a stream gauge in this location, so we needed all the parameters for that watershed so that we can model and monitor the water flow and sediment flow for different land use scenarios. So let's just erase all these layers. Let's display the orthophoto so we can see it's an agricultural watershed. So the land cover changes quite a bit. Now we will display the boundary of that contributing area. And to understand how this boundary relates to topography, we will represent the topography as contours. And let's just display them in white color. And so you can see that we have that valley in the middle, and the boundaries of that watershed really go along the ridges, and those ridges are really along this road on this side. And let's just display that outlet. So here is that point, and we can output the resulting map. And you may want to add or also a scale. Let's just add the scale bar. And then to actually provide the answer to the question, we can run r.report. So I'm not going to show the result. The watershed area is actually this category 1. So you should look at what the number there is. You should evaluate, is it a realistic number? Have I done it correctly? And then put it into your report. So you might have seen that the flow accumulation for this from r.watershed that is using single flow direction D8 algorithm was quite artificial. So let's look at some other algorithms, other options that we have to get more realistic representation of flow pattern. So I'm rerunning the region here. You don't really need to because we are in that region. Let's just double check. As you can see, it didn't really change. And now we will be running r.flow command. And this command has algorithm that is using infinite number of directions. So we refer to it in the lecture as D infinite. So let's see what the output will look like. So the computation runs a little bit longer because it's more complex algorithm. And you can see that the pattern of the flow is more realistic. We don't have this strong bias towards the X and Y direction or the diagonals. With this command, we can also trace flow upslope. So let's look at what it actually looks like if we trace flow upslope. So you can see that you are essentially getting an inverted image of the flow accumulation. And let's create the final output and answer the question, what is the upslope and downslope flow routing associated with what kind of landforms? And we are really looking at ridge or valley. So let's just clean this up. So this is our downslope flow accumulation. And when we combine it with contours, and here are the vector representation of flow lines, then you can conclude that really the flow accumulation is the highest and converges in the valleys, little valleys that we have in this area. So let's just save this for our report. Now we will erase everything. We will display the flow accumulation upslope. And let's look at how it relates to contours. So you can see that for the contours, from the contours, that it is associated with ridges. And you can also answer this question by displaying the flow upslope and downslope flow accumulation over a three-dimensional representation of elevation. And to do that, just keep only elevation data in your layer manager switched on and use the flow accumulation as color within the 3D visualization. So let's just save this. So now we will look at back at our watershed whether we have any better option within that module or within that tool to create more realistic flow accumulation. So you have seen that the single flow algorithm didn't produce very realistic flow accumulation, but our watershed by default is running multiple direction flow accumulation. So let's look at how that result looks like. So now this is much better result from our watershed when we use slightly dispersed flow where the flow is distributed between the downstream cells. So it doesn't go into a single cell, but it goes to multiple cells. And that also helps with flow routing on shoulders where we have dispersal water flow. So now again, we will create a map for our report, and we have displayed here the also the official stream. That's this red line. You can see that it matches very nicely with the extracted stream, except for this location where we have an elevated road, and this official stream actually goes through the culvert of that road, while the least cost path goes around that location because that location is slightly elevated. So it is really trying to find the lowest point to cross the road. And there is an optional task that where you actually address this issue. But for this, let's just output the multiple flow direction result for our report. Then let's go back and look at our original single flow direction. Let's overlay official streams. Again, you can see that the main stream actually fits very nicely with the official stream. It's really just these smaller flow areas, concentrated flow areas that have artificial pattern. and we still have this issue with flow over the road. So let's save this. So now you should have, in your report, you should have the infinite directions algorithm output, you have single flow direction output, and you have multiple flow direction output. So 3 flow accumulation maps. So please put them into your report and compare them next to each other. And then you can easily answer the question that is in the assignment. So now let's combine the flow accumulation and the contributing area derived from the flow accumulation with slope to compute the wetness index. And just to make it more convenient, it is essentially a map algebra expression. And what you need for that, to do that map algebra expression, you need to compute the flow accumulation, which we already did, but you would have to compute also the slope for this area, which we probably already have in our data sets. But to make it more convenient, there is the tool RTOP IDX, which essentially does this for you, so it is more automated. And we are computing the wetness index because this index is very useful, for example, when running machine learning. And it has, there are several papers that show that it is one of the most important variables when mapping ecosystems, when mapping moisture distributions, and so on. So let's look at how this looks like. So this is the output of the wetness index, and you can combine it. You can change the color table here. I have used water. Now you don't have the, let's see, it's just displayed again. You don't have the legend in the instruction, but please add it there. So we can just put it here. And let's just put also the scale bar. Oh, scale bar is already there. Okay, let's just move it here. Okay, and now we can output this map. And the final task would be creating a map of flooded area using a simple algorithm that spreads water level at given elevation around based on the topography. So we will keep working in this region. So I'm setting it up. You can skip this. And then what we will do, we will use these coordinates of this location to plant a seed and spread water at the elevation of 113.5 meters. And now let's just display it over elevation layer. So for this elevation, only this little, because our seed point is in this location, only this little area got flooded. So let's just save it. Let me remove this. And we can add the legend for the... And this tells you, the map actually shows you the water depth of that flooded area. So it's about 80 centimeters. And let's just save it for the report. And now in your assignment, you are supposed to rerun the same flooding algorithm for the increased elevation of 113.7 meters and then 115 meters. So you will just pick up the command and you can just change the elevation of that flood here. Okay, I already have. Don't forget to change the flood to flood 2. So now you can see that water elevation is spilling over that road because we have increased the water level. And then at the very end of this assignment, we have we actually show how we can mitigate that impact of that road on flow routing that I have shown before. And so you can try to do it. It's very simple. And you can just with that carving into the DM, you can shift the flow routing through essentially the culvert instead of having RDOT watershed tracing the flow around. Okay, this is all for this assignment.